I don't think so. Is it? Testing. And I'll turn on the projector.
Okay, I will do it now. No, I will do it.
Projector?
Uh,
Okay.
The projector, yeah, I will do it first.
Okay, great.
The
Yeah, okay, good. You know how? Yes?
display controls, projector, and the screen down.
Good. I.
And you said, Rohit, what should I do now? I want tablet right. I don't.
Testing. It's working now. It's working. Yeah. Great. No? Thank you, John.
So he says run timing.
In case, right.
So he said there are 3 settings, but you know that, right?
Yes.
Mic
Yeah, right.
stand.
Oh, that I don't know.
It's working. So.
Yeah.
Yeah, it should be on my here.
On mic, right?
Mic, yeah.
Yeah.
I think everything is
Yeah.
fine.
Okay.
Okay, let's get started. This will be lecture 15. As usual, a quick review from last time. Last time we talked about networks, physical networks, multiple nodes of nodes, each of which is a Markovian Q. And we introduced Burke's theorem, which basically said that the output of an MMM system is Poisson. And that's true for a sequence of such networks as well. Jackson network is a little more general. It lets you go backwards and forwards around the network any way you want. You come in at the rate gamma I from any node. With Rij, you move from node I to node j. And basically, if you don't go to another node from a given node, that means you leave. The traffic being handled by node I, we call lambda sub I. It's the external traffic plus all the internal traffic. And the beautiful result is that we found that the distribution for a number across all n nodes, the joint distribution, is equal to a product of distributions, one for each node, where each of those distributions is a solution to MMM sub I, with input lambda I, which we just calculated up here. Beautiful result, very strong. We then moved on to a special case of closed networks, which meant that you never left. In this case, you have a certain number in the system, say capital K, and you bounce around. In that case, the joint distribution of the number across the n nodes is given by this equation here. Once again, it looks like a product form solution, just as we had up here, with particular cases. And we gave the equation of how to find g of k, which is a normalizing constant, to make sure the probabilities add up to 1. And these betas, excuse me, and these x's need to be found. The x's are very much like the lambdas. Excuse me. And the solution involves a calculation very much like pi equals pi p, where p in this case is the set of numbers Rij. That p is the probability going from node I to node j when you leave node I. A small comment, we also talked about local balance, where we said if we have a general birth-death process, if we look at the red inspection method, we get what are called usually the global balance equations. But we could also look at the blue inspection methods, and those become what are called the local balance equations. And not always, but often enough, the local balance equations are satisfied. Not always. If your system does give you a local balance equivalence, then solving the local balance is easier than the global balance. And of course, you've got to check when you're done that it satisfies the global balance. If you get the global balance equations, it doesn't necessarily mean that the local balance are satisfied. You've got to check for that. Okay, that's the major review. Next, we moved into chapter 5. Now, finally, we are letting go of our neurotic holding on to exponential. We're going to let the exponential go. It gave us some wonderful results. The memory list was very important. And now we're going to enter land where we have a general distribution for the service time. And we'll go on to general service into arrival time later. And the first thing we're doing, is to talk about something called the paradox of residual life. And I pointed out that it's a counterintuitive result. And it says the following. Suppose we have a sequence of automobiles arriving. Here they come. And the time of arrival of the cars is tau sub k. And let's assume that the car coming in time, tau k, is called a sub k. And somewhere along there, a hippie arrives in red. And that hippie will get on the next car that comes along, car AN, from when he or she arrived. And it turns out that the interval, which we call the lifetime, it's denoted by capital X here, does not have the same distribution as the typical interval between car arrivals. And that's basically the paradox of residual life. We're going to go through it now. So let me identify some of the important terms. The hippie arrives at some time in some interval. The time until the next car comes is what's called the residual life. It's the remaining life until the next car arrives. Where does the word life come from? Well, the original application was testing the lifetime of light bulbs. And they had a whole bunch of light bulbs on a board with power. And they screw them in, and the bulbs would eventually fail. And they measured how long the life is, the lifetime of the bulb. That's where the word life comes from. And the way they wanted to get a statistic as to how long these light bulbs lasted is they would point to a random bulb at some point in this experiment and ask, what's its lifetime? Well, there's a residual. Until it breaks, until it fails, is the amount of life remaining. That's called the residual life. That's why the blue thing is called residual life, and we denote that by capital Y. And by x0, we call it the age of the bulb. This is how long it's been alive. And its overall lifetime is capital X. And the point we're going to make, of course, is that X is not distributed the same as these intervals. But that's where the names come from. We're mostly concerned with residual life. Why? Well, when we come into a queuing system, what might we find? We might find it's empty. We might find it's got some people in it. If it's got at least one person, where is that person? In service. And you wonder, how long am I going to have to wait for that son of a gun in service to finish? What is his residual life? So that's why residual life is important for MG1. Everybody in queue has a regular life. They're going to enter service on their own. But when I come in, what kind of a person am I going to find in service? Somebody who's been there for a while, perhaps. And if some people spend a tiny amount of time in service, others spend a very long amount of time in service, which ones am I likely to find when I arrive? The ones who spend a longer amount of time. Because the little ones are in or out and they're gone. I'm unlikely to arrive just when they're in service. And that's the source of this paradox, namely that the lifetime, the green, is different from the regular lifetime. So let's get some notation going now. First of all, let's talk about a regular arrival, an arrival that comes from tau k to tau k minus 1. So I want to let capital F of x be the probability that the time between tau k and tau k minus 1, a regular interval, is less than or equal to x. These are the regular lives. Those are the ones typically given here. And that's the capital P, capital D, capital F. That's the distribution. The density, little p df, is, of course, little f of x. And that's a differential of capital F with respect to x. Okay, so that's first thing. And now the hippie's going to arrive at a random time. Okay? Let the interval in which he arrives is this green thing, capital X. Okay? So let x be the special lifetime, namely when the hippie arrives. How long is it? And further, let capital Y be the residual life, okay, for the hippie. I'll say specifically until next car arrives for the hippie. Now, renewal theory talks about these things. We're not going to go into it in depth, but you may find these considerations when you look into renewal theory. So let me give a notation for the distribution of capital X. We're going to call it, with no surprise, capital F sub capital X of little x. And that's the probability that this random variable capital X is less than equal to little x. That's the distribution. And for y, I'm going to let a different notation. I'm going to use this notation F with a hat on top of little x. And that's the probability that capital Y is less than equal to x. The residual life is less than equal to x. And its density will be little f sub hat of x, where after that thing, that's the ddx of capital F of x. And as I indicated elsewise, this quantity x0 in this picture in black here is, if you will, the age. It's equal to the lifetime, the special lifetime, minus the residual life, and that's called the age, as I indicated upstairs. Now we want to solve for the density of x and y. That's our goal. And as I said, it's our capital Y, or capital X0, is not a typical one. Now, I'm going to give you an intuitive derivation for the density of the residual life, one that makes sense, but you really have to go deeply into renewal theory to get a formal proof of it. So here's the intuitive proof, or intuitive derivation, if you will. Now, the length of this chosen interval, capital X, the one he arrives in, is going to be proportional to its probability as well as proportional to its length. The longer it is, the more likely you're going to fall into such an interval. So I'm going to make that observation. I'm going to say that the density I'm after, little f sub x, not the residual life, but the distribution, the density of the lifetime, is equal to some constant k times x, proportional to how big it is and proportional to its probability of taking on a certain value, namely little f of x dx. Remember, little f of x is the density of the typical interval. But I'm likely to hit it with proportional to little x. Now that's the intuition part, okay? So let's write down what that left-hand side is. That's the probability that capital X lies between little x and little x plus dx, in the limit, of course. And the thing on the right is this linear weighting, and the capital K is needed for normalization. So let's write down what the right-hand side is. That's capital K. In fact, let's be a little more careful. If I've got this distribution here, then I can write down that the integral from 0 to infinity of f sub x, the special interval, integral of the density, is going to be equal to k times the integral of x, f of x dx, over the entire range 0 to infinity. Now while I'm there, what is the left-hand? I'm using this to find k. What is the left-hand side? Not expectation. Look more closely, yes? It's 1. It's a total density. So left-hand side is 1, okay? And now you've probably answered what's on the right-hand side. She's correct. The right-hand side is what? it's the mean of the usual one, right? So let's write down as that's k times little m1, the first moment. That means k is equal to 1 over m1. Done. It's there to normalize this density that I put in the top of the page so that it integrates to 1. Okay. So then we get that little f sub x of x is equal to, getting rid of these integral signs, now x, f plane of x divided by m1. I just put in k1. So that's one equation. But now let's find the residual life. This was the lifetime. Let's find residual life. Suppose I'm given how long the lifetime is. Given that the lifetime is equal to some number x, then I can say the following. The probability that the residual life is less than or equal to some amount y, given that the lifetime is equal to x, is equal to what? Well, remember now, this is a random look. The cars were arriving from a Poisson process, remember. Okay? So what's the likelihood that knowing how long the lifetime is, that the amount remaining when somebody arrives is a certain amount? Remember, Poisson arrivals take a random look at the time axis. So they're equally likely to form anywhere on that length, little x. So the probability of capital Y going there is simply little y to x. And that's, of course, 0 less than or equal to y less than or equal to x. So there's two parts here. One is the fact that the chosen interval is proportional to the length of the interval. And secondly, that the residual life is uniformly chosen over the interval x that we had. So let's look at the joint density now. And by the way, it's easy to get confused as to which density I'm talking about. You got to watch the subscripts and the hats. Okay. Joint density of the lifetime and the residual life is the following. The probability that little y less than or equal to the residual life less than or equal to y plus dy, and that x lies between x and x plus dx. That's the joint density. Now, what's the density on y given x? I just told you. It's y over x. I'm taking the density, not the distribution. So it's dy over x. That's the first piece. And the second piece, I already know from upstairs, is proportional to x. Let me write that out. That's x, f of x dx, over m1, which we just calculated for k. Well, son of a gun, the x cancels very nicely. And what I get is that this thing is equal to, oops, let's change the color, f of x dy dx over m1. And finally, let's integrate. Let's integrate over x. So I'm going to get that f hat, the thing I'm after, the residual life of y dy, is equal to the integral. X has to be at least as big as y, if that's the residual life, on up to infinity, of f of x dy dx over m1. Now let's get rid of the dy, and I get that the density of the residual life, f hat, of y is equal to, well, take the dy out of the integral, and what is the integral from y to infinity of little f dx? That's the cumulative from y. Basically, that's 1 minus capital F of y over m1. And that's the result. That's the main result. That says that the residual life density is related to the typical duration as 1 minus its cumulative over the mean. Yes? X is the total lifetime. It's the green thing.
Okay.
It's the one he arrives in.
Okay.
It's got to be at least as big as y once I choose it.
Okay, that makes sense. And so when you write earlier that the probability that y is less than or equal to y given x is greater than x, are you arguing that like you essentially look at the total lifetime of the person and then the residual life is the ratio of the probability that y is less than or equal to y.
The hippie arrives randomly in this interval whose length I've said is x.
Yeah.
Okay?
Yeah.
He can arrive anywhere there.
Perfect.
So the remaining piece is y over x.
Yeah. Okay.
Okay. And again, I said this is an approximate derivation. You notice it with a little bit of hand waving. Yes? No. No. This is densities. Now, I haven't chosen anything. This is a variable y. And this guy here is the density of the residual life. So it's some function that's f sub hat of y versus y. So y has no particular value. It could be anything. And I'm asking for the density. And it's related to the underlying distribution of the original intervals through this expression, 1 minus the cumulative. By the way, I may or may not have pointed out that, and let's take it aside here. Just a moment, let's make this prettier. Suppose I have a probability distribution function. And what does it look like? Whoops, that won't work, so I better draw it loose. So this is some distribution. I'm going to call it, I hate to use f now because it's going to confuse you. Let me call it a g of y versus y. What's the limit on the left? Y goes to minus infinity? 0. And y goes to plus infinity? 1. Great. Now you know how to calculate the mean. How would you calculate the mean from this? You differentiate it, multiply by y, and integrate. But there's another way, which is, I think I've shown this. If not, I'll do it right now. Let me draw this line right here, which is at the value 1. Turns out the mean is equal to, let me call this the red area, and let me call this the blue area. And the mean, expected value of this variable, let me call it, I hate to use y, but I will, is equal to blue minus red. The blue area minus the red area is the mean. Turns out, you can prove it very easily. I think it's even a homework assignment. It's very nice, by the way. It gives you a feeling for what the mean really means. You can see in this picture, the mean is negative, isn't it? Because there's more red than blue. Okay, well, you look up here, what we have, this 1 minus f of y is like a blue area. Right? The blue is, this is the distribution. Above that is 1 minus f of y, just a notation. But you don't have to know this, just it's a nice little tool to have. Okay. So now let's, in fact, put on some definitions. Let's use the fact that sigma squared is what? The second moment minus the first moment squared. So we can say that the residual life, well, before we get there, I'm sorry, I jumped. Let me erase this, sorry. It turns out that the age has the same distribution as the residual life. So let's just say that. We're not going to use that. But the age, which we called x0, has same distribution as y, the residual life. And the moments, which you really want to get at now, the moments of the residual life can now be calculated from the expression I have. And by definition, the nth moment, which I call r sub n, is equal to the expected value of y to the n. And remember that we had this moment m sub 1, that was for the typical interarrival time. Remember, so I'm going to remind you that m sub n is equal to the expected value of tau k minus 1 to the nth power. That's the typical interval, not the one the hippie arrives in. Yes? Not really. I just pointed out that the numerator 1 minus f of y is something related to the mean of a typical distribution. This is not the mean that I've written in the red box here. I haven't integrated 1 minus f of y, right? So it's a coincidence. Excuse me? F hat of y is the residual life density. The density of this thing in blue. And I'm defining r sub n to be its moments. And I'm reminding you, first of all, that the moments of the typical interval, one like this, that interval has moments I'm calling m sub n. Nth moment of that is m sub n. That's what I said down here. Okay. Now, if we use the moment generating properties of our transforms, we remember, or should remember, that A star differentiated n times, that's A star of s, but at the value 0 is equal to minus 1 to the n times the nth moment of whatever A star is for, okay? And I'm using A because, in fact, those typical intervals, the tau k minus 1, were basically interarrival times. That's what I'm thinking of. I'm going to apply that in a few minutes to the MG1 system. So I'm using A star as an example. But you remember this moment generating property, okay? So once we apply that to the expression we have in terms of this expression in red up here, we get the following. That r sub n is equal to the n plus first moment of the typical interval divided by n plus 1 times the first moment, m sub 1. And in particular, the first moment of residual life is therefore m sub 2 over twice m sub 1. And both of those are of importance to us, especially this last one. So let me put that in circles as well. We get that by differentiating the densities transform. Okay. So now to pick up where I started before, remember that sigma squared is equal to second moment minus the first moment squared in general. That means that this first moment of the residual life, we know it's equal to m2 over twice m1. You can write m2 as m2 minus m1 squared. I'll give back what I just took away in a moment, over 2m1. Add back what I put in there, which is m1 over 2. In other words, I added in this term, which is just m1 over 2, and I gave it back. And that implies, because what did I cook up over here? I purposely cooked up the variance, didn't I? Just to get another expression here. So R1 is equal to half the moment of a typical interval plus the variance of the typical interval over twice m1. Now I'm going to anticipate needing this a little further down in our discussion today. So let me play with it for a moment. Again, for Poisson arrivals, and where do I have Poisson arrivals? Certainly in the hippie paradox, but also, what am I studying here? I'm studying mg1. I'm going to be using it. Those are Poisson arrivals. So that's where I'm interested in looking at what happens with Poisson arrivals, taking advantage of this R1 expression. We know that R1 is equal to, and I'm going to look at the residual life of somebody in service. So first of all, I know for Poisson arrivals to a service distribution whose distribution is B of x, that R1 is equal to the second moment of service over twice the first moment. That's exactly what I wrote up here. It's m2 over 2m1. And let me recognize that with Poisson arrival, what do I usually use as a notation for the rate of Poisson arrivals? Lambda. So let's multiply upstairs and downstairs by lambda. So that's lambda, second moment of service time. And what's lambda times x bar? It's rho, utilization factor. Okay? Now, let's think ahead, and I'll come back to this later. I arrive to an mg1 system. I'm curious, how long am I going to have to wait for the guy who's in service? I mentioned that a few minutes ago. Well, if there's a guy in service, I'll have to wait his residual life, which is what I just wrote down. But what's the probability there is somebody in service when I arrive? It's the fraction of time the system is busy. If it's busy, there's somebody in service. And what's the probability the system is busy? Yes, which is rho. Rho is the fraction of time the system is busy. So that means that this thing, which I'm going to define now as W0, we're going to see this later, I'm going to define this to be the residual life of customer in service if someone, if someone is in service. I'm going to put that in parentheses. So writing that out, if somebody's in service, it'll be the thing I wrote in the line above, namely it's lambda, second moment over twice rho. What's the probability somebody is in service? Rho. So multiply by the rho, and the answer here is lambda, second moment of service over 2. And that's going to be the expected time I have to wait for anybody that could be in service. If he's there, I wait this amount. The probabilities there are just rho, so this is how much I wait. So we're going to see this symbol W0. It's a very important number. It's on average, when I arrive to an MG1 system, how much do I get hurt by the guy in service? Whether or not, if he's there or not. Was there a question? No? Okay, just scratching your head. Okay. That'll cost you 2 points on the final. Okay. Okay. So, end of the story of residual life. Again, understand that the guy you find in service is most likely have a service time that's longer than the typical one, because you tend to arrive with big. I gave you the example the other day when there were 2 kinds of inter-arrival times, 0 and 2 seconds. Half the time it's 0, half the time it's 2. So somebody arrives, next hour maybe comes in half the time immediately, half the time again immediately, half the time again 2 seconds away. So a bunch of zeros and a bunch of 2s. I come in at a random point on this axis. Where am I going to come in? On a 2-second interval. I can't come in on a 0-second interval. So I'm going to come in. So what's the average length of the interval in which I come in? It's 2 seconds. But what is the average length between arrivals? Half the time it's 0, half the time it's 2, it's 1. So, and that's why I've used the intuitive argument. You tend to come in longer, you can't come in tiny ones. You're more likely to come in huge ones. Which means the light bulb that I'm testing, it's a false test. The statistic is wrong. Because the bulb I happen to walk out and pick, it's more likely to have been there. One that's got a very short time, it's gone. I never get a chance to notice it. So that way of testing, it's a fallacy in statistics. It's called the paradox of residual life. Anyway, so much for this introduction. Okay. Now, let's get back to MG1. We'll get started on MG1. We talked a little bit about this before, but let's do it again. What is the state variable for MG1, which means give me all the information I need right now at time t so that I can do the best job in predicting the future no matter what other information you could have given me. I don't know what time, I don't care, what 30 customers ago look like. Right now, what do I need to know? And we talked about this, but let's extract it out of you. At time t, ask me anything you want. What's the minimal you need in order to be as good as anybody else in predicting what's going to happen in the future? Yes?
How long the customer in service?
Certainly that. We're going to call that, let's use that, let me call that x0 of t. Isn't that the age, x0, right? And what else do you want to know? What have we been looking, what's been our state variable up until now? Number of customers in the system. So let's call that n of t. This is a complete state variable. That's all the past matters to me to predict the future. There's nothing else. I don't care how many customers there were 2 years ago or 5 minutes ago or how many there are right now. But I need to know how long the guy's been in service. Why? Because that'll affect how long the statistics of how long he's going to remain there. Okay. And we've mentioned this before. This is a 2-dimensional state description. This is a discrete state. And this is a continuous state. Namely, the values it takes on, in one case it continues, the other discrete. And already that's complicated. We haven't talked much about continuous state systems. We've always talked about how many are in the system and how many is a discrete state. We talked about two kinds of discrete state systems. We talked about continuous time, namely you could change state at any time. That's continuous time, discrete state value. We talked about discrete time. You can only change on the integers. And we studied both. One involved pi equals pi p, the other involved pi q equals 0. But now we've got this nasty continuous state for the age of the guy in service. Gets messy. So we talked about last time how to take care of this. I'll remind you as if we didn't say anything. But you answered the question, are there any points in this continuous time when I don't have to tell you how long the guy's been in service, when I don't have to give you this thing? Yes? No, the guy in service may have been there for a while. How long has he been there? But you're close. Yes, when customers leave, how long has the guy been in service? I know how long. 0. Ah, that's useful. Well, is it useful? It's a nice observation, but can I use it? And the answer is yes. It's going to be very good. But let me describe what we've just done now. Let me draw a time axis here. Here's the time axis. And I'll draw a more careful picture in a moment, but let's assume these are the instants when customers leave. There were customer arrivals. I'm not interested in those. I'm interested in these points here. At these red points, I know exactly how long the guy's been in service. It's 0. But you got to tell me how many are in the system. That's a state variable. But at those red points, if you tell me what's happening in the first red point, this one, that's all I need to know in order to help predict what happens at the next red point, namely how many will be in the system. Nothing else about the past can help me. So if I can solve what's happening at those red points, then I don't have to keep track of this guy, because I know what it is. It's 0. So suppose I told you I'm going to solve for what's happening at the red points. Is that useful? You can see how I could do it just by calculating a kind of Markov chain. But is it useful? Does it help if I can tell you the distribution of number of people that are left behind by a departure? Because that's what this red thing will be. I'm looking for n of t only at these times here. That's the number left behind by a departure. Well, it's not clear that's going to help me. What good is that? It doesn't tell me what's happening at these other points, does it? So, two things. One, I'll help you remember that for Poisson arrivals, the probability that an arrival, the probability of finding k people in the system at these arrival points is the same as finding k people at any time. Poisson arrivals take a random look at the system. That means arrivals are taking a random look at the system. So they see the same thing that any random look. So we proved this earlier. But that's not enough. I'm talking about departures, not arrivals here. Okay? So, and of course, in the limit as t goes to infinity, this thing on the left we called r sub k. By the way, not to be confused, please, I can see it's nasty, not to be confused with these r's. These are the moments of the residual life. RK is the probability of finding k people on an arrival. And this thing we've always called P sub k, right? The equilibrium distribution numbering system. But now I want to define one other thing. I want to define D sub k as the equilibrium probability, well, let me put it this way, as the limit as t goes to infinity of the probability that a departure, that the number at time t equals k, with t are departure times. In other words, I'm telling you, I can find with these red dots the d sub k, the probability that the departing customer leaves behind k. That's sort of where I'm getting ready to go. But the question is, does that help me with these fellas, which I really want to know? And the answer is yes, of course. I wouldn't be bothering you otherwise, okay? So maybe a better way to write out this red thing here is that d sub k equals the limit as t goes to infinity, as I said, of the probability that a departure at time t, that's what I meant by this, that a departure at time t leaves k customers behind. And I'm sort of arguing with these red dots. I can find that for you. But let's see if it's going to be useful. So here comes a discussion on that now. As usual, let E sub k be the system state let it denote the system state when there are k customers in the system. It's a state that I'm going to jump around. When I hit state k, I say we're in state ek. Okay. Now, the only transitions from state k, I'm in state k in an MG1 system, okay? The only transitions from this state, from ek, if you will, are the following. I can go from having k, next having k plus 1, or I can go from k to next having k minus 1. Customer leaves or arrives. So let's draw that state diagram, if you will. Make a very simple one. Let's just draw a few states. State k plus 1, state k minus 1. And the transitions are usually going up by 1 only, because you get one arrival at a time, or going down, one departure at a time. No bulk arrivals, no bulk service. Unit steps only for the number in system, okay? Now, the number of transitions of ek to ek plus 1 can differ by at most 1 from the number of transitions from ek plus 1 to k. And in red, I'll say to go to ek, the ek plus 1 is an arrival. And ek plus 1 to ek is a departure. Now, after a long period of time, okay, the number of ups is approximately equal to the number down. Differs by at most 1. If I had 1,000,000 transitions, the number up minus the number down can be at most 1. So you can see that in the limit, the number of times I find the system in state K, let me use another color here, the number of times an arrival finds me in state K is basically the number of times that a departure leaves behind K. So basically I've been able to prove, and you can clean this up with a little more detail, I've been able to prove that Rk equals dk. And we already know that Rk equals pk, so glory be, all of these are equal for mg1 due to the Poisson arrivals. So what I'm about to do with these red dots is a good thing. I'm going to solve everything for you. If I give you Rk, I've also given you pk, which is really what you're after. Fraction of time there are k in the system. Excellent time to stop. Let's take a 10 minutes and we'll start again. Okay, let's get started again. Who came up with this brilliant idea of solving for only at the departure points? This guy, Lajos Takacs. Brilliant move, and you see it does this we want. What I'm saying here is that this is true for MG1. And so our two-state variable has become a single-state variable, the number in time in system at the departure times, which gives it to us at all times. And it took a complicated two-state description into a very more straightforward one state description, number in system, and discrete numbers as well. Okay, and the method that we're doing now, looking only at the departure instance, I think I mentioned this to you once before, is called the method of the embedded Markov chain. And by the way, before we were smart enough to do this, we started talking about this two-state description here. That turns out to be an example of something that we've seen before. In our famous picture here, we've been spending most of our time for Markov processes. And what is a Markov process? It says that the time between changes of state is memoryless. But you can jump from any state to any other state. If it's only the nearest neighbor, then it's birth-death. But you can jump by 10 if you want. Bulk arrivals, for example. We have now suddenly found ourselves in the case of semi-Markov processes, where they say, yeah, the PIJs are arbitrary, but the time between state changes is arbitrary. Because B of x, the service time density, is an arbitrary density. And we've successfully, so we really were faced with a semi-Markov process when we got down here. Where is it? Right here. This is a semi-Markov process, but we've converted it by this method of the embedded Markov chain to now a true Markov process. That's the brilliance of his approach. Okay. So now let's begin to develop this thing. What we're going to do, actually, we're going to go and do the following. We're going to solve for the Q length. How long is the Q length? Or the number in system. This is either in the Q or in the Q plus service. We're going to solve for the time in system. That means Q plus service. At the same time, we'll easily get the time in the Q. And we may get to something called the busy period distribution. I'm not going to focus on that right now. But we're going to go after these very important quantities. And by the way, we've usually spent most of our time doing what? Going after the Q length. How many in the system? But I'm telling you, with this approach, we'll get more. We'll get the time in Q and the time in the system itself. And we're going to start off by first finding the mean of these quantities. What's the mean number in system, the mean time in system, mean time in Q. And then we'll get the transform, namely distribution, transform of Q length, time in system, time in Q. And all of these are going to be related to something with some names on them. This is going to be something called the Polacek Khinchin equations. And I know you want to know what these guys look like. I showed it to you once before, but you should remember what they look like, so here we go. I'll put it right into the text, if you will. Takat showed up again. Let me. There. Okay. That's Felix Polacek, I knew him, and Alexander Kinchin. A Czech from Czechoslovakia, and Kinchin from Russia, of course. Okay. Not very pleasant looking people, are they? But queuing theorists tend to be stodgy and difficult. Okay. Okay, so we're going to find that. So let's lay out the landscape. Let's draw our double time axis. If you recall, there's two time axes I like to work on. Both versus time. The one on top is what's happening at the server. Remember, it's a single server. And the one below is what's happening at the queue. And we've seen this before. I introduced it when we start talking about queuing theory, introducing it again now. Okay? And of course, what is the notation we use? We let C sub n, capital C sub n, I'll put that down here. C sub n is the end customer to arrive. I should put all of this in black, so let me do that. Tau n, oops. Come on, change color, okay. Tau n is the arrival time of Cn. I've told you about this before, I'm reminding you now. Little t sub n is the difference between tau n and tau n minus 1. Namely, it's the inter-arrival time, I, A, T, between Cn minus 1 and Cn. And Xn is the service time of Cn. Now clearly, little tn and little xn, that sequence of numbers drives the system. People arrive, people get served. They join the queue, etc. We're going to look for some quantities, like I told you, the numbering system, the timing system, the timing queue, for which we're going to generate variables. So we already have variables for the numbering system. We call it P sub k. Okay? So let me write that down as well, and then we'll finish the picture. So I'm going to say plus the things we're looking for, namely, and I'm going to write this in blue for me, Q sub n equals the number of customers left behind by departure of Cn. And in green, because it's going to appear on the picture in a moment, I'm going to let the new variable V sub n be the number of customers arriving during the service time of Cn. So let's draw that in the picture up here. First of all, let's look at Cn minus 1 arrive. Say he comes in here. And let's assume he goes into service at some point. There was somebody in the system when he arrived. Assume he goes into service, oops, at some point over here, say. So this is Cn, oops, minus 1. By the way, at what time does Cn minus 1 arrive? Almost. Almost Tn. Tau n minus 1. That's correct. And suppose this guy leaves, say, right here. Now, of course, of interest is our favorite customer, Cn. So I'm going to draw him in red. Okay. Suppose he comes in, say, at this point. I want to do that with a nice clean line. Whoops. That's customer Cn. What time does he arrive? Tau n. And of course, then, what is this interval that I'm drawing? Little tn, that's right. You've seen these pictures before. I want to get you comfortable with them. Now, Cn arrives. Let me put a little arrow on him. When does Cn go into service? When Cn minus 1 leaves, which is, I've shown you up here. So at this point in time, our customer, our red customer Cn, goes into service. And if I draw a line here, what is the interval I'm identifying now? Waiting time. That's how long this guy, number Cn, waits in the queue before he goes into service. And I'm going to identify a variable for that. I'm going to call that W sub n. So I'm going to put that down here on my list. W sub n equals the waiting time in queue for Cn. Okay. And let's assume our friend leaves some point in the future, let's say right here. This is Cn. Then what is the interval I'm drawing now? The red interval I just identified. Xn, his service time. That's how long he was in service, right? So let's recognize that. And while I'm at it, let me draw a couple of more lines here. He arrived here, and he left here. So pray tell, what is this new interval I'm identifying? Total time. When we have a symbol for that, it's S for system time, okay? Little s sub n. And I'm going to write that down here. Little s, I'll write as a script. S sub n is total time in system. For C sub n. Okay. And let's assume the next customer that comes in, I'll put this guy in black now. Suppose the next guy comes in over here. Supposed to be black, come on. Suppose the next customer comes in here. That's customer Cn plus 1. What is this interval that I'm starting to draw here? What could you call, what happens in that interval? Idle, right. When Cn left, it turns out he left behind an empty system because nobody went into service there. The next guy came in after he left. So this is an idle period. And what I'll call an idle period. And by the way, what's the average duration of that idle period? And what is its distribution, in fact? What's the PDF for that black period? Now, that's a probability of an idle system. But what's the duration? There's a density for this idle. How long does the idle period last? This is mg1. From the time the last guy left, Cn left, yes. That's a rate. I want the density. I want the name of the distribution, a name you've had for weeks now. Exponential. Remember, it's Poisson arrivals. That idle period doesn't care when it began. It's going to be exponential because it's Poisson arrivals. So we already know the answer for the distribution of idle period. We don't know the distribution of the busy period. That's a whole other story. It's a beautiful story which you may or may not get to enjoy. Okay. Now, so let's now go to blue. Blue represents what? The number left behind by the departure of Cn. In fact, if I put a little fat little dot here and identify that Qn is left behind. And that blue dot I drew should have been drawn red because it's the embedded point in time. In fact, there's a few of those. Isn't there another one right here when Cn minus 1 left? How many were left behind by Cn minus 1? No? Well, no, don't look at the numbers here. In general, I'm sorry, you're right. Qn minus, right. I trapped you. Qn minus 1 left behind, etc. So those blue dots, that they used to be red and now they're blue, those are the intervals where I'm going to find the distribution of these numbers Q. But look, there's a little green thing here. Vn is the number of customers arriving during the service time of Cn. And I'm going to draw that here. The service time of Cn, I've drawn as Xn. During this interval, Vn arrive. During the service time of Cn. Okay. Small comment. dk, the friend we were after before the break, is equal to the limit as n goes to infinity of the probability that Qn equals k, namely the probability that a departure leaves behind k. That's what dk is in equilibrium. And we want the following along the way of our getting our solution. We want the quantity Pij, which is the probability that the next guy, Qn plus 1, leaves behind j, given that the previous guy left Qn equal to I. These are the transition probabilities among these states in this embedded chain. Now note that Qn plus 1 less than Qn minus 1 is impossible. You can't leave behind more than one less than the previous guy did. He left behind a certain number. You go in, yes. I said less than Qn minus 1, not more than. Yes, it can be much more. You're quite right. Good point. Good point. You're thinking. That's good. Okay. So I'll write that down, what you just said. Qn plus 1, in fact, is greater than or equal to Qn minus 1. If, in fact, well, I'll show you, it's possible not impossible, but it's possible, basically, for all values due to arrivals Vn plus 1. Okay. So the thing we're really after is to track the number of departures. And what I've drawn, well, what I'm going to circle now, these numbers Tn and these numbers Xn drive the system. We're looking for things like the Qn's, we're looking for the waiting times and the system times. In order to get that, we need to figure out what the Vn's are. Okay. Okay, so let's define a probability transition matrix. Let capital P be the set of those Pij's. Okay. It's a matrix of these numbers Pij, and that's for I, comma, j, comma, equal to 0, 1, 2, etc. And I'm going to make a definition now. I'm going to let alpha sub k be the probability that Vn plus 1 equals k. So let's write down what P looks like. Big matrix. Now, can I go from state 0 to state 0? The last guy left behind 0. Can the next guy leave behind 0? Qn was 0. Can Qn plus 1 be 0? That's what this entry right here would be, correct? 0 to 0. Is that possible? I left behind 0. Next guy left behind 0. Yes. Can you tell me what the probability of that is with the notation I've introduced here? Let me tell you what it is. It's alpha 0. Probability, nobody arrived during the next guy's service time. Somebody leaves. He leaves behind nobody. Next guy comes in. He has a service time. He leaves. If nobody arrived during his service time, there's nobody there. So you go from state 0 to state 0. Okay? How do you go to this next term? How do you go from 0 to state 1? And what's the notation for that? That's alpha 1, right? It's probability that one guy arrived during that service time, and so on. Alpha 2, etc. Let's go to the second row. Can you go from state 1 to state 0? Last guy left behind 1. Next guy leaves behind 0. And what's the probability? The answer is yes. What's the probability of that? Guy leaves, there's one guy left, he goes into service. Exactly, it's alpha 0 again. And so this row is the same. Now we go from 2 to 0. Last guy left behind 2. Can the next guy leave behind 0? No way. Okay? So that's a plain old 0. That can't happen. You can go from 2 to 1. Guy left behind 2, and that guy goes in, he leaves. He can leave behind 1 if nobody came in while he was being served. See, this is the physics of the problem, ladies and gentlemen. You got to think. Nobody's going to give that to you for free. You got to set the problem up yourself. So this is alpha 0 and alpha 1, etc. And so it goes. Okay. So that's our probability transition matrix. Okay. Now, let's look at Pij. For j greater than or equal to I minus 1, exactly how many have to arrive? I started with I. I'm going to go to the next state, j, greater than or equal to I minus 1. The answer is simply j minus I plus 1. In other words, last guy left behind I. So there's that many there, right? So how many must come in? More. So some come in, but take away the I. And one more because one guy left. So put some numbers. Suppose I is 4 and j is 10. What must have happened? There were 4. I leave, okay? So 10 minus 4 plus 1 more, okay? I need 7. Just think the numbers through, okay? People leave, people arrive. And when must they arrive? Of course, in the service, in the service time of x plus 1, of n plus 1. Okay. So let's draw the state diagram for these changes, okay? Let's draw the state I minus 1, the state I plus 1, the state I plus 2, and some state j. Well, from state I, can I return to state I? That's not a good picture. Can I go from state I to state I, for one thing? Yes, with what probability? Alpha 1, exactly. One guy left, one guy came in. Stay there, okay? So from I to I plus 1, you know what that's going to be? That's alpha 2, and this is alpha 3. And way over here is what I talked, it's alpha, it's what we talked above. It's alpha j minus I plus 1. But there's someplace else I can go from state I. I can go down to I minus 1 if nobody arrived. So you can see all the alphas are represented in this picture. Yes? No, these are probabilities. These are not rates. Oh, well, we're going to balance probabilities, though. Yes. because you're going to get the right answer again. What are we going to do with this? Inspection method. Okay? Okay. So let's talk about finding the alpha k's, okay, before we go to the inspection method. The arrivals are independent of the system state. Let's say that. It's Poisson arrivals. Xn is independent of the system state. And is distributed as capital B of x. So this quantity of interest V sub n only depends upon the distribution of Xn. I mean, that's what the alphas are about. The alphas are about the probability of Vn taken on certain values. So it only depends upon the distribution of Xn. And also in parentheses, and not on n itself. Poisson doesn't care how many in the system is going to come in, whatever it likes. So I'm going to get rid of the subscripts n. At least for this calculation. That means xn as a random variable will be written now just as x tilde, a service time density. And the probability of xn being less than or equal to x is going to be written as the probability of x tilde less than or equal to x, which of course is what notation? Capital B of x. That's what we mean by capital B of x. And V sub n, the number of arrivals during the service, doesn't depend upon n, so we're going to write that simply as V tilde. So the probability that Vn equals k is the probability V tilde equals k. And do we have notation for that? The last thing I wrote down? What's at the very top of my page? Notation for the probability V equals k is alpha k. So let's write that down. So this is alpha k. So let's try to find out what alpha k is. That seems to be essential here. So alpha k, as we know, is the probability that V tilde equals k. And I'm going to use my usual trick. I don't know how to calculate that right offhand, but if I condition it, I may find an easy way to specify it. So let's, in fact, assume that it's basically a joint distribution. It has to occur with some value of service time. So we're going to integrate for x service times of all possible values of this probability I'm looking for, V tilde equals k, and x tilde is less than or equal to x plus dx. All of that little dx. Now, what probability law did I use to write that down? That's a joint probability, but there's a law for this. I'm saying if the event V equals k occurs, it's got to occur with something else. all possible other something else. This is the law of total probability. And what I wrote down here are all the possible cases for the service time I'm dealing with, because I'm integrating all of them. So this integral is really the sum of all the probabilities of how v equals k can take on. X can be 1, could be 2, could be 3, could be pi, could be whatever. Now I'm not done yet, because I want to write now the trick of using conditional probability to write down this joint probability. So I'm going to, let me just say, using conditional probability, I'm going to rewrite the joint as follows. That alpha k is equal to this integral from 0 to infinity of this joint, which I'm going to write as a conditional. If I write a joint as a conditional, joint A and B equals A given B times the probability of B. So let's write that down. So this is the probability V equals K given a particular value for X. And what's the condition? That X tilde does equal X, which is B of X dx, right? So the B of X dx is the condition that goes along with the condition I put on the first thing. And of course, little b, as you know, is the density related to the distribution capital B. But we have Poisson arrivals. V comes from Poisson arrivals. How many arrivals in the service time? V. So the probability that V tilde equals K, given that the interval of which I'm calculating is X, namely X tilde equals X, is equal to the Poisson distribution, namely it's lambda X to the K over K factorial e to the minus lambda X. That we knew from before. So I can finally write down that alpha K is equal to the integral from 0 to infinity of what I just wrote down, lambda X to the K over K factorial e to the minus lambda X B of X dx. I'm going to circle that in red. Oops, that's not red. So now this unknown alpha k is written in terms of things I do know, the lambda and the b of x. So basically this gives me p. Why? Because P is composed of these alphas that we wrote up here in the matrix. I know the alphas now. Let's make a notation. Now let's note the following. Alpha k is greater than 0 for all k greater than or equal to 0. That means we can reach all states from any state. So we have an irreducible Markov chain. And of course, I'm going to define our good friend rho equals lambda x bar, some of the input parameters. And the chain is ergodic from what I just said. If rho is less than 1. It doesn't blow up. And I'm going to assume rho is less than 1 and what follows. Now, how will I find dk? Well, I just told you a few minutes ago that dk equals rk equals pk. So I find pk, I found dk, which is the whole idea. Now, how am I going to find it? Give me an equation, a vector equation. I'm tipping you off what it should be. Pi equals pi p, except it's p equals pp. And of course, p, the vector, is p0, p1, etc. Okay, so we're ready to go. We set it up. We have an approach. It doesn't look trivial because there's a fairly complicated p matrix. So the first thing I'm going to do is try something a little less ambitious. Okay? First, let's find the mean Q length. Not the distribution of number, but the average number. For mg1. And this is our task for the next little bit. Okay. Now, I need to write down a symbol for the limit of Qn. I'm going to let Q tilde equal the limit on n of Q sub n. And by the way, don't forget, this is first come, first serve. When I start talking about times and system, I better specify what the order of service is. I haven't mentioned that before. Okay, so what I want to do is I want to relate Qn plus 1 to Qn for two cases. Case 1. Case 1, Cn leaves behind a non-empty system. So let's draw that. I'm going to take and draw my double time axis again. I'll do it down here. Again, this is the server. This is the queue. Okay, let's watch Cn come in. I'm going to put Cn in black this time, if I may. Cn comes in at some point. He goes into service at some point. And he leaves. Now, the guy I'm after is Cn plus 1. He's a guy of interest. Suppose he comes in somewhere here. He'll go into service when Cn leaves, so he goes into service right here. A little while later, he leaves. And the next guy Well, let's identify a few things. Let me label these guys first of all. This is Cn plus 1. And this is Cn here. Now, how many are left behind when I'm pointing? Clearly Qn by definition. Qn left behind. And similarly, over here, Qn plus 1 left behind. Service time here is xn plus 1. And I guess I should do this in green now. Let me mark. This is a dashed line, actually. How many arrives in here? Vn plus 1. Whoops. Using the notation from before. Now, if that's the case, I want to write down Qn plus 1. Qn plus 1, in this case, is how much? It's equal to the number left behind by Cn minus 1 because I'm leaving, plus the number that arrived while I was being served. And this is for the case Qn greater than 0. Now case 2. Cn leaves behind an empty system. Let's draw the time axes now. Cn comes in, goes into service, he leaves. Cn plus 1 comes in after that because Cn left behind the 0. So Cn plus 1 comes in here. As soon as he comes in, he goes right into service. A little while later, he leaves. So let's label these things. This is Cn plus 1, Cn plus 1, Cn, and all the rest is, that's Cn plus 1, I'm sorry. And all the rest is Cn. Tough class up there. Okay. The number that arrive in this interval here is Vn plus 1 again. So in this case, Qn plus 1, the number left behind by Cn plus 1, given that Cn left behind nobody, is equal to what? Vn plus 1 is the ones that came in while he was there. He was there all by himself. Okay? So again, these are the two interesting points. Nobody left here. Vn plus 1 left here. So I'm going to mark down that Qn, just to remind you, Qn equals 0 right there. and the Qn plus 1, which is equal to Vn plus 1. So we finally reach this final equation for today. It says the following: that Qn plus 1 is equal to one of two things. It's either Qn minus 1 plus Vn plus 1, and that's if Qn greater than 0, or it's equal to Vn plus 1 if Qn equals 0. And we'll stop right here. I wanted to get to this point. That is the defining equation for the numbering system. Number left behind by departure. And we have to work with this equation. And it's a beautiful way in which it's dealt with. And I'll leave that up for your enjoyment on Wednesday. Tonight, I'm going to assign the next homework assignment. It'll be due next Sunday night. By the way, did all of you notice that the assignment 6 was due last night? Because I thought I announced it, but it seems I didn't. Anybody here miss that it was due last night? Again. Okay. How long will you need to get it done? Okay, deal. I won't give out the answers yet. Not that it's a big secret, but sure. But you get the new assignment tonight for next Sunday. I should check how many people actually turned in the assignment already. Let's see, do I have that here? Yes. 9 people handed in the assignment plus those, that's 12, 13, 3, 6, 9, 10, 11, 12, 13, 14, 15, 16. Some of the readers are not handed in. They don't get scored here. Okay. Do your homework. You know, we're not checking it that carefully. It's good for you. Makes you do good on exams. Okay, see you on Wednesday. Beautiful results come out of this. Don't worry. It looks like it's messy now. It's beautiful results. You'll really enjoy it. Thank you.